My name is Arvid, and today I want to talk about refactoring C++ using LibTooling. So let's get started. Before we start, I want to get everybody on the same page here. So what is refactoring when I'm talking about refactoring? For that, let's have a look at what Wikipedia is saying what refactoring is. So that's a quote from Wikipedia. It reads as follows. Code refactoring is the process of restructuring existing computer code, changing the factoring, without changing its external behavior. So, in essence, whenever I change code while still preserving the original behavior, rather the original output, that is considered refactoring. So, for example, outlining. We have a block of code in a function, and we factor this block of code into a new function. And instead of this block of code, we now call the function instead. Or the opposite. Inline, we have a function, we remove it and factor the function body instead of the function call, and that is refactoring. Building a better abstraction. For example, you have a compression API, maybe libz, which is written in C. And you want to have it more object-oriented or more modern, so you build an abstraction on top of it. So we refactor the old usage of the C API into the new usage of the C++ API. Or you change an algorithm to, for example, improve the performance. Those are all tasks of refactoring. However, today I want to focus on automated refactoring. Automated refactoring is all these tasks of refactoring which can be carried out by tools. They require no human interaction beyond just invoking it. And you may know already one major automated refactoring tool, and that is ClientID. It does, beyond invoking, everything for you. But it still leaves us with the question, why do we want to automate in the first place? So let's assume I'm a library author. I'm running a library, maybe a UI library or something, and I want to deprecate some old code. I have a function. I want to deprecate it. So what you do, assume, use the newly introduced C++ attribute to deprecate the function and to build a replacement. So like use XYZ instead. And you keep the function around and maybe you remove it later. So the question is, how long do you keep the function around? A year, 2 years, 5 years, 10 years, forever? Unfortunately, the answer is often forever. So you want to keep old code working, right? Backwards compatibility is important. That makes deprecation and migration rather difficult. For example, deprecation in C++ takes like over 9 years. Stored auto pointer, deprecated in C++ 11, and only removed in C++ 17. And even though it's removed, you can technically still get it. So is it really removed? For that, the term live at hat has been coined. This has been coined by Titus Winters, who works at Google. He presented a plenary at cppcon 2017, which was called C++ as a live at hat language. He proposed a technique to avoid the woes of semver originally. Remember semver? We have this semantic versioning where we have like given the major dot minor dot patch, we increment the major version every single time we make an incompatible API change. We increment the minor version when you add functionality in a backwards compatible manner, and we increment the patch version when we make a backwards compatible bug fix. Sometimes there's like suffixes added like slash dash alpha dash def, something like that, to distinguish further builds. However, what constitutes a major change? Is it a break for just me? Is it a break for everybody? Is it an easy migration? What something is a break for one user may not be a break for another user. Not everybody of a certain library, not every user of a certain library uses all of the functions available. So that makes major version bumps in package management, for example, really difficult. Titus then introduced the notion of a nonatomic API migration. So a nonatomic API migration for users, basically, as a library author, you build a new API. And you build a tool and you distribute the tool to do the migration for the user. You wait for the user to apply this tool. And after some time, you remove the old API. The timing can be varied. So for example, you can say to your users, you have 1 year, you migrate, and then we remove the old API. Over this presentation, we will learn how to build a tool just like that to carry out API migrations just like described. An app sale, the library which is built by Google, has started building those tools just recently. You can see a screenshot of ClientID. It's in the Clang tools X repository. And as you can see, AppSale started building tools to do these migrations for their users. They distribute them via ClientID. And they're among a couple other names which you may know, like Android, Boost, Bugprone, cppcon guidelines. So they're certainly in quite good company. At almost the same time, I personally came up with the same technique. Even though I don't do non-atomic API migrations, I do atomic API migrations. Since the team working on our code base is quite small, we can deprecate and remove in the same atomic commit. That means we remove an old API, we build a replacement, we build a tool, and we commit all of that at the same time. That means our code base can keep moving forward while still staying relatively stable. So before we dive into building, let's have a little look at an example. So in this example scenario, we are building a UI library. So in this case, for example, we are building a UI library for our in-car entertainment system. We want to build this tool, we want to build this tool to the presentation, which will do this API migration for us. So to start, we have a class called button. This class is created via either two of the factory functions, create button or create button X. Create button is, as you can see, quite a mouthful of a function. It takes 5 parameters, 5 arguments, 4 of which are ints, and 1 of which is a C string. It's something we kind of want to avoid. For that, we built a new function called create button X. Takes no arguments, just returns us a new button. We can then use the API on the button itself to configure it. This is relatively easy to grasp, but it's relatively hard to carry out manually. And it's not just 5 lines of some sort of tool. So this is a little more complicated. Here's an example usage. In this case, we're building a dialog. For example, we want to go into overdrive mode in our car. We want to have an OK button for that. We create the button to the create button X with a create button X function. Sorry, create button function. Can you still remember which came first? Is this a button which is 32 pixels by 32 pixels at position 150 at X and 40 at Y? Or is it the other way around? So it's easy to mix up dimensions and position here. This is a button which is anchored at X32, Y32, 150 pixels wide, 40 pixels high. The replacement is this API. We just call create button X, and then we use the API on the button itself to set the position, to set the dimensions, and the title. It's a little more code, granted, but it's pretty obvious to see at first glance what's happening here. It's much more descriptive and quite a lot cleaner. And I'd reckon it's a little less bug prone as well. So that leads us back to the title of this talk. So far we've been talking about refactoring, but we haven't been talking about LibTooling. This has been ignored more or less completely. So what is LibTooling? LibTooling is part of the Clang and LLVM compiler suite. So LLVM, you can think of LLVM as more or less as a library built for building compilers. And LibTooling provides us with access to the Clang internals. That means we can get parsing for C++ and semantic analysis. It is used to write Clang tidy, Clang modernize, Clang rename, and a couple of other Clang tools. And since it gives us direct access to the Clang internals, we can do everything which the C++ compiler can do as well. That's a lot of power. What requirements to build a tool like that and to apply it to our code base? And there's a big requirement, which is your code able to compile with Clang? This is something which I've previously underestimated quite a lot. I just assumed everybody writes more or less standard C++, and we can all compile with Clang, and we're all happy. It's usually not much of a problem if you're developing, for example, with GCC on Linux. Maybe much more of a problem if you're coming from Visual C++, or if you're in the embedded space or certain console compilers. You may use some language extensions which are not available in Clang. So I was curious. I asked my Twitter followers whether their code base compiles with Clang. And I gotta be honest with you, the results surprised me quite a lot. 73% of all the participants said their code base compiles with Clang, which is awesome. But 27% said their code base doesn't compile with Clang. There were roughly 150 participants here. And I have to give a little disclaimer here. My follower base on Twitter goes a little into the game dev direction and general C++ dev, often with focus on Linux. The reality in the embedded space may be quite a lot more skewed towards the no than the yes. And this is something which has to be kept in mind. Leading us to the next point is the build system. To properly apply one of the Clang tools, we need a build system which can generate us a compile_commands.json. The compile_commands.json is a so-called compilation database. It contains every single file in your project, and it contains the flags required to compile this file. So everything from -std C++14 to fastmath, please don't do that. Yeah, so the tooling knows how to build your project, essentially. These can be generated with CMake, for example, or Ninja has the -t compdb. And there's Bear, which is sort of a hook between your compiler and your build system. Basically tell it to invoke Bear instead of your compiler, and it will generate you a compilation database out. Recently, Clang itself has gained support to generate you one of these databases. You can pass -mj in uppercase letters, and you'll get out a JSON, which has the format for a single file. And with some SED script magic, you can format it into one large file, and you get your compilation database out of that. At the end of the presentation, there's some bonus slides. Those provide you with links to a more in-depth explanation how to get your build system to generate a compilation database and what you can do with it. Not just this Clang tidy tools. You can run quite a lot of the LibTooling static analysis tools as well. So, unfortunately, it sounds all far too good, right? We can have easy migrations without having to bother about it, and we can do that fairly automated. That's true, but it's not a silver bullet. We have to assume we are having well-behaved and sane code. If we have well-behaved code, we can assume that tools should provide us with an easy way to do these migrations. And the focus here is on should. Unit tests, for example, or tests in general, are quite important as well. If you can verify that one of the migrations you did work with your unit tests or your integration tests, that is great. If you just apply them and you sort of hope it works, that may not always be the case. And we will see an example of that a little later into the talk. And again, this is absolutely great for Nonatomic API migrations. So, but, there's always a but. There's Hiram Slaw. Let's not forget Hiram Slaw. It's another term coined by Titus Winners, unfortunately. And it's named after Hiram Wright. He's also an engineer at Google. And basically is saying that every single time you build an API, all of the observable behaviors will be dependent upon. So we assume, back to our example, like create button, may do some other work beyond just creating a button. And maybe some user depends on it. Then you do the migration to create button X, and suddenly that user has broken code. So you really have to be careful what you're doing with your migrations. Even though they're automatic, and even you assume that you build a replacement for an old API, which is 100% doing the same thing, it may not be. So you've been warned. So let's get a little into it. But first, quick summary. The code needs to compile with Clang to be able to run the LibTooling suite. You should, or rather need, a build system which can provide you with a compile commands.json compilation database. And if possible, have some tests. And even better, have some sane code. With that, let's head into the setup of LLVM. So, it's a little bit of a lie, actually. I will skip the setup. The resources to explain how to set up LLVM and how to set up ClientID or LibTooling are plentiful on the web. I have provided in the bonus slides again dozens of links to get you started quick, as well as a slide where you can just copy paste the code into your terminal and you get a working LLVM setup out of that. The slides will be available after the talk on my website. That is arvid.io, arvid.io. And today, for simplicity, I decided to not implement a whole LibTooling tool from scratch, but to plug into ClientID, just like AppSale did, to create a new custom check, which will provide us with all the right tools and migration APIs to do our migrations. That leaves us here. Standalone versus ClientID. So why did I choose ClientID here? ClientID is easy to get started. There's, again, plenty of resources on the web to get started. The entry is definitely lower. And with standalone, you have to build some of the APIs which are in ClientID on your own. For example, ClientID provides us with an API to do quick fixes, these migrations we want. You can just say, here's some source range, and I want to replace this source range with this string. And you're good. It does it for you. You don't have to open any files. You don't have to write any files. You don't have to bother with IO streams or C file API or whatnot. It's all built in. And you're in good company since, as we've seen before, AppSale uses ClientID as well. I personally, though, I use a standalone tool, which may now sound weird why I would say that. And the reasons for that are quite different. And the major reason is that my projects live in Perforce as opposed to any other version control system. And if you know Perforce, it requires manual checking out. And since all the files are by default not writable, you check it out and then you can write it. So my tool, for example, checks out all the files. And once the migration is done, it creates a commit on its own and puts all the files which have been changed in there with some automated messages. Makes it a little easier for me. But to get started, ClientID is great. It provides us with all we need. So we now have set up ClientID. We have set up LLVM, and we can get started implementing it. There's two functions we need to implement: register matchers and check. We will start with register matchers. Register matchers is used to register, as the name says, all the matchers for our AST. And they're written in some sort of little DSL. This DSL is called simple AST Matchers. It's implemented as a mix between like functional macros and templates. It looks sort of like the algebraic data types you can find in functional programming languages, and provides us with a very powerful but simple and conscious way of describing AST patterns. So the AST I'm calling here is, just to explain quickly, is the abstract syntax tree. That is a data structure in the compiler which represents our C++ source code. It is generated by the C++ frontend of Clang, and then it is passed around and maybe manipulated until it's later generated into some sort of IR. In this case, in LLVM's case, in Clang's case, it will be LLVM IR, which is then consumed by the backend to generate code. We don't care about the code generation here. We just care about the AST, and we care about matching it. The matchers take n amount of arguments and return as a new matcher. So they basically will end up as a long list of function calls. These matchers are type safe. That means if you want to build a matcher which doesn't work, so for example, you are looking for a function declaration in a for statement, it doesn't work, you'll get a type error. And there are basically three different categories of matchers. The first category of matchers are the so-called node matchers. Node matchers match a specific type of AST node. They are at the very core of every matcher expression. They need to start with one of those. They are then further refined using the two remaining categories. We'll get to that in a second. They take, again, an arbitrary amount of arguments, and all of these arguments act as an implicit all-off. We will see what that means in the third category. They are the only matchers which support the .bind call. .bind is used with one string argument to retrieve these nodes later down the road. So if we want to examine nodes later in the check, we need to bind them first in the AST matchers. Examples for node matchers are function decl, which is matching any function declaration. So for example, we have our own function declaration of create button, which we then need to further narrow down with a narrow matcher, which is the next category of call, which is called hasName. And they're call expressions, which is matching, as the name says, any call expression. This may be combined with, for example, the function decl to find a call to a specific function. Then there's, for example, compound statement, which is matching any compound statement, so function bodies, for example. Binary operators, matching any binary operator, like plus equals or minus equals or just equals. They won't match overloaded C++ operators, though. There's a different matcher for that, so be careful. The next matcher are narrowing matchers. Narrowing matchers are used to match certain attributes on AST nodes, thus narrowing down the current set of being matched nodes. So for example, narrowing matches are the previously aforementioned all off, any off, and a couple of others. Those are special logic matchers. They take any type of matcher and return the same type, so you can combine them in a very special, very powerful way. Then we have equals. So we can use equals to, for example, examine an integer literal and figure out whether this integer literal has exactly the value 42. And there's isConst, which is taking no arguments and just narrowing down all non-const, or rather removing all non-const functions from the set of matches. And we have hasName, the previously mentioned, which is next. We have traversal matchers. Traversal matchers specify a relationship to other nodes reachable from the current node. Examples of traversal matchers are hasDescendant. So if you have, for example, a function, compound statement with hasDescendant, you can iterate over all the descendants of this compound statement. And we have hasElse, which is matching the descendant nodes of an else in an if statement. Has LHS, has RHS, short for left-hand side and right-hand side. This is matching the right-hand side or the left-hand side of an operator. We will use that with the previously mentioned binary operator. And for example, callee as well, which is matching the callee of a call expression, used to find out an explicitly named function call. Let's start by building a simple matcher to get everybody accustomed to these matcher expressions. It can be a little complicated. So here we have a for loop. We're going to try matching all for loops which have a new variable declared in the init part of the for loop, and this variable is then declared to 0, initialized to 0. We start this by matching a for statement. This is, if we would have this as a matcher in our ClientID check, we would get back all the for statements in our program. And this is again a node matcher. You will see a pattern emerging here, because now we are adding traversal matchers, has loop init, or rather in this case actually it's a narrowing matcher, has loop init. And we're matching a decal statement, which is a node matcher again. Then we have another narrowing matcher, has single decal. And then we have var decal, just get another node matcher. And you can see the pattern here. We're alternating between node matchers and narrowing or traversal matchers. This allows these AST expressions to be almost read like English sentences. So we can say, for statement has loop in it, then a decal statement has a single decal, and then a var decal, and so on and so forth. So next, we found all for statements. So now we found all for statements which have a loop in it, and those have a single declaration inside. So for example, for and then just int I, no initializer. So we need to find the initializer as well. This is done using as initializer, yet another narrowing matcher. And then we again another node matcher, integer literal, and the previously mentioned equals. And here again, we are just matching all variable declarations which have an initializer equal to 0. So now that we have that, we need to get access to it in the check itself. For that, we use the mentioned bind call. So in this case, we call bind and give it some string identifier. The string identifier is completely arbitrary. We can put any string in there we want. Here I've decided for loop is quite descriptive, and we just went for for loop. Oh, and if you've ever wondered how people can read Lisp, this is how people can read Lisp. You just have colored parentheses. Quite useful, actually. There's some plugins for most of the other editors out there. Yeah, so with that, let's get back to implementing the check we've discussed in our example previously. Remember, we have the create button call, and you want to replace this create button call, or migrate this create button call into create button X. First, for that, we create a matcher for our function declaration. Same pattern here. We start with a node matcher, then we have a narrowing matcher. In this case, has name. So this matches all function declarations for a function called create button. We will use this little matcher later in the main expression. The main expression is rather big and complicated. This is matching all assignment expressions which have a variable on the left side and a function call to create button on the right side. And this is where I will mention how important this same code is again. If you see this and you think about the function call to create button, you realize that it won't match any function calls to create button which do not have, where the return value is discarded. So in our case, we assume that any function call to create button will assign the return value to some sort of variable, even if it is just a temporary. So this is important. We could build a matcher which matches both cases, but in this case, I've decided we assume all of our code is sane, all of our code is correct, and there's no function call to create button which is ignoring the return value. So let's walk through the big assignment expression here. We start by matching a binary operator. Then we try to narrow it down by matching exactly and only operators which are called equal. So this won't match all equal binary operators. However, again, this won't match any of the overloaded operator equals. So if a function operator equals overloaded, this won't match it. This is not a problem here, since our create button is returning a pointer. And you can't overload operator equals for a pointer. So works for us. Next, we get the left-hand side and we get the right-hand side. Those are the previously mentioned has LHS and has RHS traversal matchers. In has LHS, we're using another traversal matcher, anyOff. And anyOff again takes arbitrary amount of arguments and will match if exactly one of those is matching. What we do here is we try to match either a decor ref expr or a member expr. And this is interesting because we just have an assignment to a variable. Yes, I thought the same until I looked at the AST. If we're assigned to a member variable, which is our case here, we have m_button, there's an implicit this dereference in front of that. So this is a member expression. If you're just assigning to a local variable, you will have a decor ref expr. This means we need to match either of these. Once they're matched, we assign them, or rather we bind them to LHS. And it's perfectly fine to bind them both to the same identifier, since they can't appear both at the same time. We can just use the same identifier to get them into check. On the right-hand side, we match the call expression, where the callee is our previously created create function matcher, just above, in the line above. We will also bind the call expression to call, since we will need it later. With that done, we bind the whole thing to OP. And the bind returns us the new matcher expression. This matcher expression can then be added to the ClientID matcher using the addMatcher function. addMatcher expects a node matcher and a callback. The callback here is our selves. Since this is in ClientID, and this is one of the benefits you'll get from ClientID, you don't need to implement the whole callback mechanism which is expected. You can just pass this here, and the class will do everything for you. So, pardon me? So the question is whether we can give the matcher a specific name. No, you can't give the matcher a name. However, when you create a new ClientID check, you will give your check a name itself. So you can use this name to distinguish the check in the ClientID command line. And there's a Python file called addNewCheck you can invoke, which creates a check for you and gives it a name and all these things. Does that answer your question? All right, perfect. So this might still be quite a little bit of magic. And matching AST expressions is definitely quite a lot of experimentation. There's a little bit of reading the docs required. And for that, I can absolutely recommend you to dig into the AST Matchers.h file, which is the header file defining more or less all of the matchers you can have access to. Another great way is to just use Clang itself to examine the AST. For that, Clang has the -AST-dump flag, which you can pass to Clang itself. To do that, you need to pass -x Clang before that, since you need to circumvent the Clang driver, as well as -f syntax only to avoid any undefined references from the linker later. If we look at the result from dumping the AST of our, in this case, we're dumping dialog.cpp, which contains the code snippet we've seen before. if we look at the dump of that, we can clearly see that we have a binary operator here. The binary operator has, or is of type equals. This is exactly the binary operator we've matched earlier. If we look at the first descendant of our binary operator, we have member expression. And this member expression, as you can see as well, is m_button, our variable. The second descendant of a binary operator, since it's a binary operator, we have two descendants all the time, is a call expression. And it's a call to a function returning a button pointer. And if we look at the descendants of this call expression, we can see that it is calling a declrefexpr, which is a function called createButton with this function signature here. And if we further dig into the call expression, we can see all our arguments. We have 4 int arguments, 4 integer literals with each their values, and we have a string literal also with their value. And you can also see it's of size 3 because we have 2 characters and 1 null terminator. With that said and done, we can go further and implement the actual check. Check is called every single time one of the matchers has found a match. It's called exactly once for every match, so you don't need to do any looping or anything else. You can just build all your code into check, and then it will be called for you. In check itself, first we grab some utility classes, and you reject any matchers which are not in C++. This may sound odd at first, but I found that certain matchers I wrote match some of my Objective C++ and Objective-C, so I made sure that only C++ may be matched here. This may not be the case for you, so you can either remove it or match just C or just Objective-C++. All the languages which can be compiled with Clang. Next, we'll get the nodes which we found in the AST matcher before. For that, we use the strings as identifiers we've created in bind, or created with bind rather. Once we've gathered these, we need to make sure that they are the correct type. The return value of getNodeAs is explicitly typed by the user itself. That means if we want to get anything back, we need to make sure it's the correct type. And we don't throw, but we get a null pointer back if the types don't match. And to catch any errors the programmer may have done, I'm just asserting here that we're not getting any null pointers back, and all the nodes we assume are there are actually there. It's just purely for us to make sure any programming errors are caught early. So now we need to grab the correct left-hand side expression. Since we have, remember the AST matcher, we had either member_ref decl or declref. We need to make sure that we get one expression out of that. And we just check whether which one is null, and we use the other one. And since they're both expressions, we can cast them into an expression and use the expression node later. So next we have a simple helper. This helper is called catark. Catark is using the lexer to get the string from the source of a certain argument at position I. We will use this to generate the strings we will insert later, since we do everything as strings here, kind of. Once we have that, we get into the territory of cosmetics a little bit, actually. And what we have here is we are making sure that all the lines we insert after the create button call are correctly indented. And since this is usually not needed, but in this case it is, since we're inserting new lines after a function call or after a replacement. In most cases, you can get away with just replacing some code, and you don't need to worry about indenting or other things. Here we do, and I kind of wanted to have like beautiful code and not get ugly code out. You can skip this if you, for example, have Clang format or uncrustify running over your code base and just say, migrate it and just run the formatter over it. So to do that, we first grab the column number of which our initial statement or initial call expression is located at. We are then creating a new string with just empty spaces as long as these columns before the call expression. And we're using stdfil n for that here. So next, we need to grab the expression of the left-hand side, the binary operator. The binary operator, again, was our equals, just the equals. On the left-hand side of the binary operator is exactly m_button. So the string will just contain the variable name. And again, for that, we're using the lexer access. We're using getTokenRange for that. It's a really, really useful function. Finally, we're reaching the code generation step. So these are the three function calls which will replace our old createButton function. And as we see here, we're starting with a new line, and we have this indentation string, which is, again, just empty spaces as long as the indent was. In our cases, it's going to be probably 4 spaces. Then we have LHS string, which is just m_button. And then we just some string, which is our function call with the arrow operator, set position, having a pointer. And then we're using the previously created lambda function, or helper, to get the string, get the arguments as a string. In this case, set position will be get arg, and set position will be 32 and 32. In set dimension, we will have 150 as a string, and I think 40. And here in set title, we will have OK. So once we've done that, we need to find the position where to actually insert these. So how the migrations work in ClientID is you generate so-called fixit hints. These fixit hints require a position from you and the string you want to either insert or replace. In our case, we have 3 insertions: the set position, set dimensions, and set title function calls. They need to insert it right after the previous function call. So we have createButton as a function call, and then right after that, we need to insert it. However, we can't just use call, get, and lock, because, well, it's just the call, which means the semicolon is not going to be included. If you just would insert it after the call, you would insert everything before the semicolon of the previous statement. To get around that, we just ask the lexer to give us the next token after the call, which is going to be the semicolon. So for that, we use lexer : find next token, and then we assert that we actually found the next token. And the bool cast here may look a little odd, but find next token will return us an optional, which means we need to check whether it actually is filled. So with that, we can actually start generating our diagnostic. To generate a diagnostic, ClientID, or rather the class we're implementing this in, has a member function called diag. Diag will generate the diagnostic for us in the format of ClientID's error output, or rather warning output. We anchor it, sort of, at the beginning of the function call, and we provide some description. Here we're just saying, this is deprecated function call, don't do it, we have a fix. And for the fix, we create the previously mentioned fixit hints. These are the 3 fixit hints we need to create. And these are the strings we just created a couple minutes ago. Set position string, set dimension string, and set title string. They will be inserted all at the same location, at the same token after the call, just the semicolon, after the semicolon, to be specific. This may look odd, but the insertions are queued in a way, which means each insertion is inserted one after another. So multiple insertions at the same position will just queue one after another and create a beautiful function call. And to round everything up, we need to replace the original createButton function with our newly created createButtonX. And since we remove all the arguments, we can just write it as a string in here and don't worry about it. So now we can compile and run our new ClientID check. We invoke ClientID just like you would invoke any other LibTooling-based tool. And as you can see in the command line here, we have disabled all custom or all default checks using the dash asterisk. And we've enabled, which is the namespacing you mentioned previously, or you asked about previously, is custom dash asterisk. This is my namespace in ClientID, where all my custom checks are living in. And we're running it over all the source files in our project. In this case, we just have button CPP, dialog CPP, and test CPP. If you run it, we get the pretty familiar output from ClientID. We see here again, we're generating a warning at dialog.cpp line 6, column 16, which is the create button call. We can also see which of our dash line break here, sorry, which of our checks has generated this warning. And we can also see the description we put in there. And since we've already set dash fix in ClientID, ClientID will migrate it automatically with the previously created fixit hints. And it will notify us about this by saying fixit applied, suggested code changes. And then we have just the summary here with this, which is basically saying, hey, we found some warnings, but we applied a fix for you. And with that, I want to thank you, and thanks for having me.